the solution to the great ecological crisis humanity is facing right now. So the objectives of this presentation are the following. I first give an overview of the current paradigm in energy generating devices and its frontiers. Then I represent the Spintronic engine as a limit breaking device. Afterwards, I will present my experimental results and demystify their inner workings through the theoretical models I developed. The talk will be split into 4 parts that will tackle the following questions: how to make an engine, what is the Spintronic engine, how does it work, and in conclusion, what comes next. First, what is an engine and how can we build one? So, we all know about many machines that produce the electricity. Disparate aims at giving the basic tools of thermodynamics, which is the framework lying behind the science of engines and depicts the controversies that challenge the core principles of the theory. So we all know about many machines that produce the electricity we use in our daily lives, for example, a dam, a solar power, a nuclear power plant, etc. And all of these machines need 2 necessary ingredients. So first, an energy source that may be gravitational, mechanical, chemical, thermal, or electrical, and then a converter. So the energy source may derive from what's called the potential gradient, which is a thermodynamical force that is applied on a working substance that is usually a kind of fluid that is experiencing some transformations due to this thermodynamical force. And then the converter is used to convert one energy from one form into another form, which is exploitable and from which we can use to produce a desired action we call work. And so this converter is like a turbine, a solar cell, or a fuel cell. And for example, in the case of the hydraulic turbine, the energy source we use is the gravitational potential energy of the water that is running downstreams. And so this gravitational energy is rotating a turbine, which is converting this energy into electricity. And so we have the energy input E that is coming from this fluid that is converted. Part of it is converted into work that is used to do an action, and some of it is converted into a fatal energy called heat. And so with this concept, we already touched into a central concept of physics, which is the conservation of energy, basically stating that there is no free lunch. And this principle is at the center of the first law of thermodynamics, which states that formally states that the internal energy of a closed system does not change, and for an open system, this energy decomposes into part of work, and part of heat. And then this principle is accompanied by a second law that limits the kinds of time transformations that is allowed for a system, and that is allowed in nature, and that is giving an arrow to time. And basically, it states that a broken glass cannot remodel and fix itself, and that heat flows from hot to cold. And formally, it states that every closed system equilibrates if you wait long enough, and that this equilibrium is reached when the state has a maximum entropy, which is a quantity that quantifies the disorder of the system. And so, in the case of engines, this law is translated into maximum efficiency, which is called the Carnot efficiency, that limits the amount of energy we can extract from a heat engine operating between 2 temperature baths. And so for about 2 centuries, physicists have been trying to derive these laws from the microscopic laws, and but so far they have failed, in particular for the second law. And this has brought physicists to try and break these laws. And the first of which being Maxwell, who designed this famous experiment of the Maxwell demon. So take a box filled with particles, and then divide this into 2 parts, and imagine a small trapdoor that is placed between the 2. And so a demon may open the trapdoor and let the hot particles to the hot reservoir and block all other particles, which thereby exerts some kind of sorting, such as the hot becomes hotter and the cold becomes colder. And And so this sorting goes against the second law, and so the daemon acts as an asymmetric high-pass filter. And so this daemon uses the information of the particle to sort the boxes and separate hot from cold. And then this experiment has been generalized by Szilard, who designed an engine with this based on this maximum daemon. So take a box, and then it works in 4 strokes. First, take a box at K1 equilibrium, then divide it into 2 parts. You will have more particles in one box than in the other, such that you can place a piston facing the hot bath with the higher number of particles, and this piston will move, and so you can harvest this the movement of this piston and convert it into mechanical work, and then finally you can remove the barrier and start the cycle again. And so these paradoxical experiments then found a resolution with Landauer, who solved them by giving a cost to information, and this cost is linked to the erasure of the memory of the daemon, and this erasure is limited from below by some quantity that is linked to the thermal bath that is used to erase this memory. And then, related to this issue of Maxwell's daemons, the issue of nonlinearity, well illustrated by Feynman's Ratchet and Paul in his lectures on thermodynamics. And so, to illustrate this law, Feynman considers a ratchet that is able to rotate only in one direction because of the pole. And so he asks this question: can the thermal motion of the particles that embed this ratchet, called the Brownian motion, can it be used to rotate the ratchet and produce mechanical work? And so what he showed in a not so careful analysis, that he showed that if the temperature of the ratchet is identical to the temperature of the vane that is used to harvest the work through the load, then this cannot work as an engine, and you cannot produce work from it. And it can only work if you have a temperature gradient between the ratchet and the vane. And then this experiment has been extended in the field of electronics by Brillouin, who considered a circuit with a diode and a resistor. And here the diode only allows the current to flow into one direction, thereby acting as the ratchet and pole. And the resistor is a device which, when immersed in a bath at temperature T, delivers a stochastic white noise called the Johnson-Nyquist noise and acts as the Brownian motion of the particle. And then Sokolov showed that you cannot produce work from the system. The voltage cannot be generated. Because when you use when you study this system trivially, you can find that it generates some kind of voltage. Sokolov showed that this was not the case because you have the thermal fluctuations of the diodes that counteract the thermal fluctuations of the resistor, thereby nullifying the power if there is no temperature gradient between the diode and the resistor. And so, in conclusion, self-rectification of the Brownian noise is prohibited without a non-equilibrium resource. Finally, more recent advances in quantum mechanics have also challenged these laws, and to give you some insights into this development, let me start by giving you some basics of quantum mechanics. So quantum mechanics is based on the principle of superpositions, which states that quantum systems can behave in a superposition of states in which energy, position, and momentum are ill-defined. And this this motivated the famous thought experiment of the superposition cats, in which the quantum cat trapped inside the box can be in a superposition and be both alive and dead before you open the box and find out. And so this principle of quantum superposition can be extended and leads to the concept of quantum entanglement, which is a kind of superposition that's occurring between systems with many numbers of particles. And so quantum entanglement is a special quantum superposition in which information is shared between two correlated quantum systems in superposition, such as measuring one influences the other at a distance. So, for example, you can take two boxes with two cats, such as you can place them in a superposition in which the two cats are either both alive or both dead. And if you open the box of one cat, you instantly find that the other cat is of the same kind as the box you have, and it's the intuition is that there is no. You find that the other cat is, and it projects the other cat into one state, and you without a signal at a distance, and which is seemingly paradoxical. And so these two notions are linked to the concept of quantum measurement, which is the act of opening the box. And so opening the box meaning projecting the quantum state into a classical state and destroying the superposition. The problem, such as the cat was both alive and dead, and now it's either alive or it's dead. And now the problem is that we still do not have a proper quantum measurement theory, such as it is treated as a black box, meaning that we only care about the effects of the measurement, but not the causes. And we only know that the cause of the measurement lies in the interaction between the system and the environment and the measurement apparatus, but the precise mechanism that causes this collapse remains unexplained. And so, what these quantum mechanical concepts imply for thermodynamics has therefore led to a new field of research called quantum thermodynamics that challenges the rules of this classical thermodynamics. And in particular, it studies the strange behavior of quantum measurements and its implications for energy and entropy. And because, for example, the entropy of the delocalized superposed wave is higher than the entropy of the definite particle, which challenges the second law. And quantum measurement can also energize the system because the definite particle can have a higher energy than the average energy of the wave. And so, following this, and this quantum measurement problem raises deep questions into the nature of reality and how does it create. And following these lines of thought, scientists are not trying to explain the thermodynamical implications of the measurements, and they are also trying to build new kinds of engines that rely on so-called quantum resources that describe the real properties of the quantum world, such as measurement, entanglement, coherence, and squeezing, such as, for example, information shared between entangled states can be used by a Maxwell daemon in order to produce work. So in this context, I claim that the Spintronic engine is one such device that can potentially use quantum mechanics at our advantage to produce electricity in a revolutionary way. So what's the Spintronic engine? So in this second part, I will first review give you some context on spintronics, and then describe the architecture of the device, and present the experimental results I have obtained. So let me first start by introducing this weird quantum feature called spin. So all particles, including fundamental particles like the electron, or composites like atoms, have an intrinsic magnetic moment called spin. And spin can be represented by a vector, and the special property of spin is that it is quantized, meaning that the electron spin, for example, the electron spin projection on an axis can only have two values, plus or minus one half. And more effectively, the spin characterizes the way a particle reacts to a magnetic field, because the magnetic field exerts a torque on it, which will curve its trajectory. And pragmatically, spin is observed in a Stern and Gerlach experiments. So you fire some particles into a tube in which you have an homogeneous magnetic field, and you find out that at the end of the tube, the particles are deflected into two possible directions, which shows that this quantization of spin. And so spin is at the center of ferromagnets that constitutes the majority of the magnets you can find, for example, on the fridge. And a ferromagnet is a material in which all local magnetic moments are aligned below some critical temperature called the Curie temperature. And in this case, this ferromagnet has a spontaneous magnetization. And above this Curie temperature, these magnetic moments are random, and you effectively have no magnetization. And so, when all magnetic moments are anti-aligned, you have an antiferromagnet, which is also non-magnetic. And elements like iron, cobalt, and nickel have an unpaired spin, and so when you stack them together, they have a favorable exchange interaction, such as all magnetic moments align, and ferromagnetism emerges. So the discovery of spin has led to the field of spintronics, which leverages the spin of the electrons alongside their charge to create new functionalities in electronic devices. And this field emerged in 1988 with the discovery of the giant magnetoresistance effect by Albert Fert and Peter Grunberg, who were awarded the Nobel Prize in 2007. And this field has then evolved and improved through the engineering of magnesium oxide magnetic tunnel junctions, which marked a milestone allowing non-volatile memory solutions with ultra-low power. And it has led to the technology of magnetic random access memories, which utilizes the electron spin for data storage, and this technology has been improved with the spin transfer torque, spin orbit torque, and voltage control effects, which significantly reduced their energy consumption. So, at the center of spintronics is the magnetic tunnel junction. So magnetic tunnel junctions are stacked that, in which a tunnel barrier, an insulating tunnel barrier, is sandwiched between two ferromagnets. And this ferromagnet usually have one which is pinned, so which has a fixed magnetization, and the other one which is free, such as you can align its magnetization to the pinned ferromagnet in the parallel state, or anti-align it in the anti-parallel state. And this induces the effect of tunnel magnetoresistance, which is the change of the resistance when the magnetization of the ferromagnet is switched from the parallel to the anti-parallel state. So, with this concept in mind, let us review the results my team obtained before my arrival at IPCMS. So the first experiment was obtained on NGO junctions, for which the stack is presented over here. And this stack presents two crucial ingredients. So first, a small carbon layer that is coating the cobalt electrode, which is called the spinterface. And this coating is mainly used to allow for a narrow energetic bandwidth between the electrode and the tunnel barrier, and also to enhance spin selection. And I will further explain its special behavior in the following. And then, in the NGO barrier, you also have small carbon impurities that are making a spin chain. And the striking result with those junctions is that one of them featured an autonomous spontaneous output power of 0.1 nanowatts. As you can see from this graph, you have points in the power generating quadrant in this intensity potential graph. And so after this first breakthrough, my team looked into an implementation using molecular junctions, and so the stack is presented over here. And on this stack, the spinterface has been replaced by a C60 fullerene molecular layer, and for the tunnel barrier, the MGO has been replaced by a few layers of cobalt phthalocyanine molecules that feature the center cobalt atoms that are making this spin chain. And so with this structure, the power increased up to 100 times, reaching up to 24 nanowatts at under temperature and 450 nanowatts at 40 Kelvin. Then additional experiments revealed that the variation of the engine power output was related to a magnetic phase transition of the cobalt center. And so indeed, the phase transition at 120 K that was observed in the electron spin resonance experiments corresponded nicely to a change in the power output slope you can see on this graph. And so this provides a kind of evidence for quantum entanglement inside this engine. And then another feature is that the conductance line shape feature a kind of kink with a sub-K-T spectral resolution, such as it provides evidence for non-thermal feature. So before I show you the results of my work, let me start by presenting the basic building blocks of this engine. So it is based on three main ingredients. So first, a working substance, which is made out of the spin chain, this coupled paramagnetic centers that are trapped inside the barrier. And this working substance benefits from discrete energy levels and can be in a coherent superposition of states. And then you have the combo of the ferromagnetic electrodes and the spinterfaces, which is leading to a no-thermal bath. No-thermal bath is some kind of bath which has some special property, for example, to inject quantum coherence, induce spectral squeezing, and behave as an entropic link. And the effect of this combo is that it also lifts the spin degeneracy of the paramagnetic center trapped in the barrier. It can also select one spin channel and rectify the spin charge imbalance. And so finally, this device benefits from fast work strokes as it's all electronic, and it looks like it is based on quantum resources, such as it could extend the Carnot efficiency limits. It benefits from an autonomous feedback, and it works at room temperature. So the hopes of this technology are high, as it could lead to a high power, material efficient and reliable engine that is emitting no carbon dioxide. And indeed, by stacking these junctions in series and making a panel, if you extrapolate the results you have for the magnesium oxide implementation, it would be up to 1,000 times more powerful than a solar panel without the need of the sun. And so this could be at the very center of a desperately needed revolution that would solve the life-threatening crisis of the destruction of the environment we are living right now. And this is why I started this thesis in the first place, and this is what gives more meaning to my work besides the great physics that's behind it. And so when I joined this thesis, this project, many open questions were standing, such as what is the energy source, how it is maintained autonomously, is the spinterface needed, and what's its role. And we'll see in a moment how I managed to tackle them. And so to answer these questions, my initial goals were first to achieve routine fabrications of those devices, explore the working conditions, and work on the modeling to explain those results. So my experimental work consisted first in processing the junctions. So I worked on the oxide implementation, So I received the ground stack from Nancy, and then I applied lithography, etching, and depositions in order to build the stacks, which you can see on this chip that in the end contained 120 of these junctions, and then I put them in this big machine in order to perform magnetotransport experiments on them and analyze their electromagnetic behavior. And so I will now present to you the results I have obtained on samples that presented no splinter traces. So the first effect I observed is a memristic effect. So some of the junctions displayed two different intensity branches that could be switched on and off by applying a positive or a negative voltage. What was interesting about them is that one of the branch featured a conductance peak that could be used to encode a bit of information. Then I found a singular magnetoresistive behavior, which featured a nice peak in the magnetoresistance curve that correlated nicely with the conductance line shape. And so this behavior has not been reported in the literature so far in devices of this large size. And then I also studied the jumps that occurred at the specific biases that in which you can switch branches. And so, depending on temperature, I found two different types of noise. So, a telegraphic noise between the two branches, and one diffusive noise between that is the center around one branch. And in a statistical analysis, I studied these noises in more depth with respect to voltage, and so I observed the distinctive features. So first, dispersive halos that are believed to be linked to interference effects between at least two nanotransport paths that coexist simultaneously and with close energy and lead to these fluctuations of the current. And then also the telegraphic branch jumps that may be related to the charge and discharge of an environmental complex that is influencing the transport through the barrier, but not participating directly in the transport. So unfortunately, as you saw, I was not able to reproduce the results I was hoping for, which was mainly to find more active devices. And this failure was probably linked to the difficulty to control the position of the paramagnetic centers, and also the need for a splinter face, and it may also be linked to systematic errors that come from the difficult four-step processing protocol I had to follow. But nonetheless, I found some devices with rich behavior that revealed signals typical of scanning tunneling microscopy experiments, and additional experiments showed that the insertion of these carbons revealed conduction hotspots that are indeed supporting the fact that the transport in these junctions happen through impurities of atomic sizes. And so, after about a year of failed experiments due to low reproducibility, some machines I worked on went out of service, and so I decided to pause this research, and it led me to theory. And I quickly arrived to some results, and so I pivoted entirely on theory, and I built three models that can explain the inner workings of this engine, which I will present right now. And so the first model is macroscopic and electronic, and aims at that describing the system as a whole at the level of the electronic circuit. And the problem starts with an interrogation. What if we could produce energy from a quasi-static magnetic field, magnetic field difference between two regions? And we know that this has been notoriously hard to extract energy from a static magnetic field because of the Lorentz force, and because in this force you have the magnetic term that does not induce work. So usually to produce energy with a magnetic field, you have to rotate it, and its rotation usually induces an electromagnetic force through Lenz's law. This is what we use in turbines, for example. And so then I figured out that the two ferromagnetic layers are behaving like magnets, meaning that they have an interaction magnetic potential energy between the two, which they are trained to minimize. And so I asked the question: what if you could have a microscopic device that was trapped between these two magnets, and that could be sensitive to the equilibration of the magnetic configurations of the two layers. And so, in light of the P1 paradox on diodes and the spintronic nonlinear behavior I observed in the experiments, I proposed an electronic circuit that is made out of two spin diodes and two resistors, such as they depend differently on the spin of the electrons that's ejected to it, and so I considered their characteristic as just an asymmetric ladder. And then I connected this circuit to a capacitor, which is representing the ferromagnetic electrodes, and a capacitor featuring a non-equilibrium magnetic potential that is akin to a spin resolved electrochemical potential mu. So that's this term, and which is coding for the magnetic misalignment of the electrodes. And so I studied this problem in the framework of stochastic electronics, and I was able to derive a master equation, which I managed to solve in order to extract the electrical power, and so the current and the intensity of the device, and for realistic set of parameters, I could reproduce the results I have obtained in the experiments. So after this model, I decided to move to a lower level and use the usual framework of spintronics in order to describe the engine at the mesoscopic scale and to agree with the previous model. So I start with three materials, so two ferromagnetic electrodes and one central material, which is based again on a diode whose conductivity is reacting non-linearly with respect to the spintronic accumulation. And so I considered this bar, and I considered the small elements of this bar, and I looked at the thermodynamic forces that was applied to these small elements. And it features 5 terms. 4 of them are pretty standard, and the last one is related to a non-equilibrium magnetic field that is rotating the magnetization of these elements. And usually, in passive spintronics, this non-equilibrium magnetic field is put to 0, and it's not considered because it's limited to a power generation, as we will see. And so the free energy, along with the spin fleet mechanism and the conduction transport equations, leads to this canonical equation, which was established in the Vallet-Vert model. And using the boundary conditions, I was able to derive the voltage and the current. And so the first thing I looked at in this model is to look at the response of this device to a stochastic current. And I showed that it was indeed producing some power akin to the Beulin situations, but it was inefficient to explain the result. So this led me to wonder about this magnetic term that was set to 0 in passive spintronic and ask the question, what if a non-equilibrium magnetic field was trapped at the interface because of the combo of the spin interfaces and the electrodes? And so when considering non-zero interfacial magnetic field, this leads to a discontinuity in the spin accumulations at the interfaces, and I showed that this device could rectify this discontinuity and generate some power and reproduce the results. The question is now, what is the source of this non-equilibrium magnetic field trapped at the interface? And so I proposed a potential phenomenon that can explain this autonomous magnetic non-equilibrium magnetic potential, mainly surface currents, magnetic monopoles, magnetron squeezing, spin textures, and proximity effects. So finally, I moved again one step lower and designed a microscopic quantum model in order to explain the engine. And I started with two sites with non-degenerate spin split energy levels that are interacting through a tunnel interaction and a magnetic interaction. And I connected these two sites to electrodes that are fully spin polarized thanks to the spin interfaces. And I finally considered a bosonic bath that would flip the spin on one side. And so this led me to, in the standard Markovian approximation, this led me to a master equation featuring a non-Euclidean term with 6 terms that code for the electron injections on both sides, the whole injection on both sides, the boson and the boson pump, and done. And all of the thermodynamical forces applied to it are encompassed within these coefficients. And the problem with this equation is that when you run it to infinity, it usually leads to a passive steady state that does not generate electricity. And so I figured out that this system is embedded in a larger and noisy environment, so it's likely unstable. And so, such as this environment is likely to perform autonomous measurements on it due to, and which will destroy the superposition. And evidence points toward the spin interface, which will be acting as the measurement apparatus, since it imposes a spin referential on the magnetic centers, and it may induce periodic measurements or stochastic measurements because of the charge fluctuations that are occurring on it. And then the spin interface may also act as a daemon that is collecting information of the nearby spin and therefore inducing measurements. And so with these considerations, I proposed a simple 2-stroke cycles that will make the engine. So first, the system evolves as follows. So first, you have the thermalizing strokes that places the system in the state close to the steady state, and then this state has the property of having an entanglement between the two sides, and then the measurement stroke on one side kills this entanglement and, on average, energizes the system. Finally, during the other thermalizing stroke, the system relaxes, and through this relaxation, it emits, it lowers its energy, and part of this energy can be harvested as an electrical current, which can be used to perform work. And so I could simulate the cycle and show that it was indeed producing energy even after the cycle stabilized in a non-equilibrium steady state. And so I first showed that the energy could be generated even without a bosonic bath and with completely thermal parameters in which such as the measurement alone is the source of this the energy. So this is therefore realizing some kind of vacuum fluctuations in a way. The problem is that the power was too low to explain the results. And then I showed that the power was indeed greater when taking non-thermal parameters. So, for example, changing the coefficients, such as they feature a temperature, a spin, or a potential bath, leading to some of the order of picowatts. But the best results were obtained for thermal parameters of the electrodes, but for parameters of the boson bath that feature a non-thermal bias. And this led to a power output that was close to the experiments. And so, in summary, experiments and theory both show long-lasting continuous energy harvesting that use quantum and magnetic resources. And the three models I built correctly predict the magnitude of the power output, and they give insight into the relevant tuning parameters that can use to maximize it. And future work should elucidate and an experiment support the transport through atomic impurities in magnetic unit junctions, which reveal quantum features from single molecule junctions and STM in mesoscopic devices. And so future work should elucidate the physical origin of the nonlinearity and the steady thermodynamic forces I have assumed in the models. Then experiments should focus on maximizing the success rate through improved manufacturing processes, optimized architecture, in order to envision industrialization. And finally, the flow of information in the device must be studied in the framework of quantum thermodynamics with conserved quantity in line with the work of Joan Vaccaro and other leads can point towards this the link with spin glasses, with the electromagnetism of the interface, with the holographic principle, and with the measurement problem in order to identify the source of this autonomous measurements. And I will stop here. Thank you for your attention.